Good afternoon, everyone. So today we're going to look at acids and bases. So if you turn to page 18, 19 in your study material, page 19 has got all the definitions that you need to learn by heart. This is the way they're in the exam guidelines, so this is the way that you have to learn it and have to give it back. But it helps a lot if you understand what you're saying. So a lot of times today I'm going to ask you what's the definition, and then we're going to apply it. Because once you apply it and you understand it, then it's easier to learn the definition, right? Now, so let's, instead of looking at that page, start by looking at the second page. Right, that is page 20. Now on page 20, you find the table of all the acids and bases. See if we can find that. Right. All the acids and bases. Now, you can do nothing with acids and bases if you don't know this table by heart. You have to know hydrochloric acid is HCl and it is a strong one. Right. Nitric acid, HNO3, and it's strong. Sulfuric acid, H2SO4, there it is, and it's strong. So those three are your strong acids, and then all the rest is weak. So it's easy to remember which ones are strong, but you have to learn the formulas as well. Now, since grade 9, you've been learning the first three, because it's the strong ones, it's the important ones. You've learned all of them when you were young, and now we get on to more difficult ones, right? So the two that you might not be quite comfortable with is acetic acid, right? And you also now know that we can also call it ethanoic acid, acetic acid or ethanoic acid. And some of you will remember this because some of you learned it in grade 9, like CH3COOH. No. Yeah. So some of you know that one. That one is known to some of you. That's a weak one. The one I want to focus your attention on is that oxalic acid. Oxalic acid. That's actually one that is prescribed for your practicals. So you really have to know this because they ask it a lot, because they sometimes think you don't do the practical, you just write the report. So they want to test to see, did you do the practical? So they ask oxalic acid a lot. And what makes oxalic acid difficult is oxalic acid, you have COOH2. Now this looks really strange. Why 2 if it's the same thing? Now you've done organic chemistry at the beginning of the year, so you will be able to understand that it's got a carboxylic group to one side, and you've got the other carbon fixed onto that, and that's also got a carboxylic group to the other side. So if you look at this one, you've got 2 hydrogens over there, but you need to put the 2 there. They bonded together. It's not 2 separate ones. Otherwise, we could have just said COOH. Right. Now you have to say 2. So that's where the 2 come from. But this hydrogen and that hydrogen will be released equally easy. Right. It will be, if this one goes, that one usually goes as well. And therefore you are giving off 2. Right. So usually we prefer that top one, COOH2. But now some textbooks and sometimes even the Department of Education has started writing that the other way around so that it looks more like those. Now these bottom 2s, we call them organic acids because they've got a lot of carbon, hey? Right. So these ones are different. All the other ones are inorganic, and with them, if you give off an H, it is the one in front that's going. But when you get to organic acids, then it will be the H at the end that is leaving, right? So it's only those 2 that you have to learn by heart. They're organic, they do the things different, right? But then sometimes they take that one and they rewrite it that it looks like an inorganic one. And now when you have to write an equation, you can use either the top or the bottom formula. They will mark both, right? So Now you think, okay, I can only learn one. That's not the truth, because if you get into the exam paper, you don't know which formula will be used by the paper. You don't know if the department is going to use the top one or the bottom one. So actually, you have to learn both, right? Even if you prefer one, and I always prefer the top one. Right, that's the traditional way to write it. So you have to know both of them, right? Now, if you look at them, they are a little bit new, so let's talk about this. If you've got acetic acid, you've got CH3, COOH. If that H is removed, then you will end up with CH3, COO, negative, right? You are going to give off an H+. We'll talk about that just now. It's an acid. It's giving off an H+. If it H+ is removed, what remains is negative. And there's something else that goes wrong with acids and bases. You think the pluses and minuses are unimportant. If you leave out that minus, they leave out the mark, okay? Right. So remember, a plus or a minus is very important. A proton donor is going to give off an H+. So it will end up minus. Now, what is that called? What is that one? Acetic acid. Right. So what is the anion called? If that is acetic acid, then this is called acetate. Acetate. Right? So you can get sodium acetate or lithium acetate. So acetic acid gives you acetate ion. Right. And how about oxalic acid? If you've got oxalic acid, it's like that. It's going to give off both hydrogen. You end up with COO2. And what should be the charge? 2-, because you've given off 2H+. Right. And if this is called oxalic acid, what do we call this? Oxalate. Oxalate. Right. So acetic acid gives you acetate, and oxalic acid gives you oxalate. Right. So if you haven't learned that before, when you get to your second last page in your booklet, you will find that negative ions there, right? Oxalate and acetate. So if you are not comfortable with them, just go and look at them once again. Right. Okay, so you have to learn this table by heart, and also let's talk about the bases over here. Just 3: sodium, potassium, and lithium. The ones that will give hydroxides that dissolve completely. If you look at your periodic table, where do you find the lithium and the sodium and the potassium? Over there in group 1. Hey? And they are the ones that when you put them in water, they will dissolve. When you get to magnesium and calcium hydroxide, if you put them into water, they don't dissolve that fast. Now, actually, when you were in grade 10, you learned the table of solubility. But I know you can't remember it. Okay. So, just remember, sodium, lithium, and potassium hydroxide will immediately give off an OH- because it dissolves, and therefore they are strong. And all the rest you have to learn, they are weak. And then we get to just one that looks strange. Which is the one that looks strange of the bases? NH3, ammonia. Now, ammonia is very important. Ammonia always do things different, right? You've got all the rules, and then you've got ammonia doing something different. So whenever you see ammonia, you have to say, okay, stop the bus. There's something different here, right? And we'll see what is different. So now I'm going to look at the bottom over there. We have a small table, and I'm actually going to redo the table to explain what's happening in this table. So you don't have to rewrite everything I'm going to write, okay? Everything is down there. You can make your notations of whatever you want to write on there. So we're going to look at acids and bases. And when we look at that, we are going to talk about strong acids and strong bases, and we are going to talk about weak acids and weak bases. Can you see it's exactly that table? Right. So you don't have to take too many notes. You can listen and you can try to understand rather. Okay, so let's talk about strong acids. Give me a strong acid. HCl, nice one, and HNO3 and H2SO4. Those are the 3 strong ones. Right, now back to my periodic table. I want you to check the hydrogen over there. Is it a metal or a non-metal? Remember, you've got that step. Hydrogen being on the right-hand side of the step is a non-metal. Okay, let's go on. How about chlorine? Chlorine, over there on the right-hand side, it is a non-metal. How about nitrogen? Non-metal. Oxygen, non-metal. Sulfur, non-metal. So everything you've got here is non-metals. Okay, and now I want to take you back to grade 10. If you've got non-metals, or grade 11, if you've got non-metals bonding, what type of bond will you have? Yes. You're actually good with remembering, hey? Covalent bonds, covalent bonds. If it's non-metal and non-metal, it makes a covalent bond. And how do you make a covalent bond? What happens when you make a covalent bond? It's sharing of electrons, right? So do they just overlap, and that electrons are now is part of both of them, right? They overlap. How does an ionic bond form? You give an electron over, and this one becomes negative, and that one is positive. You've got ions, right? So with covalent, do we have ions? No. So the important thing is if it's covalent, then there is no ions present in that one. So when this one reacts with water, the very important thing is you have to put water into your equation. I have to see water in my equation because it has to react with the water in order to make ions, right? What do we call the process of making ions? Ionize. So the acids will ionize. They are now going to produce ions, right? So they're going to produce ions. How are they going to produce ions? What is the definition of an acid? It's a proton donor, and a proton is an H+, right? So the proton is being donated. It's moving over. So what do we end up? With this one, you've got HCl. If it's giving off H+, it will end up as Cl-. Cl-, right, and actually in solution if you want to be thorough. Right, what happens to the water? It receives that H+, it's become H3O+ in solution, and we call that hydronium ion. Right, so you're fine with this one. So what is very important is here you have to have the water in the equation because it's got to ionize, it's got to make ions. Now look at the other side. Strong bases. What's your 3 strong bases? Sodium hydroxide, potassium hydroxide, lithium hydroxide. Okay, back to the periodic table. Lithium, sodium, potassium, what do you know about them? Metals, right? O and H, non-metals. So here you have metals and non-metals bonding together. So this is ionic bond. And you've already got ions. So when this one reacts with water, don't put water in the equation. It's not actually reacting with the water. It's sort of drifting on top, hey? Right, there's already ions present. It's not going to form ions, so it's not ionizing. What do we call it when we take things apart? Dissociate, right? Associate is when you put them together, rain, weather, and pancake. Associate, right? If you take things apart, then it's dissociate. So what happens with bases is they dissociate. And how does it happen? So the sodium goes to one side and the OH to the other side, and they are in solution. Right. So that's why if you look back at page 19, If you turn back to page 19, there with the definitions we said, strong acids ionize completely in water to form high concentrations of H3. Weak acids ionize incompletely. So the word ionize there, because it only now I'm going to form ions. There were no ions present before. Right. Now let's go on to the weak acids. Name me a weak acid. Well, let's take acetic acid, which is the first one there. Right. Carbon, non-metal. Hydrogen, non-metal. Oxygen, non-metal. So all the weak ones, you will always also find they're covalent. So for the weak ones also, you need to put in water into your equation. And it will also now form ions, so it will now ionize. Right. And how does it ionize? By donating a proton, so you end up with CH3, COO minus. What is the name of this one? The acetate ion, right? If it was acetic acid, then you end up with the acetate ion. And obviously, hydronium ion. Okay, so if you add something to water, you will end up with something that's got charges. You end up with something that you've got ions. Right, now we get to the bases. Now there's a lot of bases. Which is our weird base? Ammonia. Right. Now all the other bases have got metals in them. It's like sodium carbonate, right? Or sodium hydroxide. They've got metals. What do you know about N? Where on the periodic table do I find nitrogen? Nitrogen is a non-metal. Right. Nitrogen is a non-metal. And hydrogen? Non-metal. So this is the only base that is covalent. Right. All the other bases that you use are ionic and they will dissociate. Right. But when you get to NH3, this one is the weird one. It is our only covalent base. And what do we know about covalent things? There's no ions present. So when you react this one with water, for this one, you have to put water in your equation because this base is actually going to ionize. Right. All the others are going, bases are going to dissociate, but this one is going to ionize. How does a base react? A base is a proton acceptor. Right. So it's going to receive a proton. So if it receives a proton, it will form NH4 plus. Remember, we receive an H plus. So there's another H, making it 4, and the charge is plus. Right, in solution. And what happens to the water? There's an H plus removed, so that will end up as OH minus. Right. So we've got our equations, and now we haven't talked about strong and weak. What is the definition of a strong acid, and what's a weak acid? Strong acid, ionize completely. Completely. What does completely mean? It means if I put 1,000 HCl molecules into the water, they will all end up with H pluses. Every single one, right? Completely means everyone will be going over. So if I put 0.2 moles per cube decimeter in, I will end up with 0.2 cube moles per decimeter, right? If I put 1,000 in here, I will end up with 1,000 over there, right? But what do we know about weak? It ionizes incompletely, right? Incompletely. So if it is incompletely, it means I'm going to put 100,000 of that acetic molecules in, and I will find 4 or 5 have gone over and made H pluses, right? Only a few of them will react to give me H pluses. So this is difficult. We don't know how many are going over. Now let's look at the top one. Remember about Kc values? What will the Kc equation look like for that hydrochloric acid? It should have been Cl minus times H3O plus products divided by reactants, HCl. Right, no water. Why? Yes, solvent, right? It's a solvent. It's a pure liquid. It's a solvent. So the water doesn't come in there. Now, if you look at that one, is that going to have a big value or a small value? Big. Because what we said is everything is going over. So on that side, you have a big number. And on this side, you have more or less 0, right? So the top one is very big because it ionized completely. Most of it end up in the product form. So then the Kc, and now we call it Ka because it's acid. And it will be very big because most of the things end up dissociated, right? And in the same way, when you look at a weak one, the Ka value will be small because only a few of them produce H+. The rest is staying put in the same original way, right? Strong bases dissociate completely, right? Means every single one will produce an OH minus, and weak ones incompletely, right? Now, if you look at the arrows, there's something that you can do with the arrows. If you look at the arrows, now the Department of Education don't mind if you put just a single arrow or double arrows or whatever. But for the guys who are going on with chemistry at university, it's nice to know there's a way that I can indicate that something is strong. If something is strong, I can indicate it by putting a big arrow to the right and a itsy-bitsy small one to the left. Right. Because most of the things will be doing that. Right. So a big arrow to the right and a small one to the left will show most of the things are going over. Right. And then how about a weak one? Then the itsy-bitsy one is to the right and the big one is to the left, showing you that the chemical equilibrium actually favors having more of these. Right. Okay. So this is the second one, the second table on that page. So I hope you all made your own notations over here. So remember, acids, they ionize, every single one of them. But when you get to the bases, it depends. All the others, like sodium carbonate, will still dissociate. But when you get to NH3, that is the weird one. It is the covalent base. And that one will ionize. So if you turn back to your definitions on the previous page, when we looked at acids, it was ionize and ionize because they were covalent, right? When you got to bases, what does it say about a strong base? Strong base, dissociate. That's what we expected, eh? Sodium hydroxide, lithium hydroxide, potassium hydroxide. They dissociate. But what does it say about weak bases? Dissociate and ionize. Who is responsible for the word ionize in that definition? NH3. It does things different because it's covalent, right? So now, when you know why the definition says that, then it's easier to learn that. Everyone up to there? Okay. And then, obviously, there's a lot of baggage that come with you. That's why sometimes you have problems with acids and bases. It's ionic tables, and then also in grade 10, you did a number of reactions that you had to write formula for. Formula and equations for a number of reactions. That first one, acid and a reactive metal, and it always produces a salt and hydrogen gas. So this metal will bond to the chlorine, and then the hydrogen is free. Right. So that was that one. Second one, acid and a metal hydroxide. What do we actually call a metal hydroxide? A metal hydroxide is a base. Right. Tell me another name that we give to an acid-base reaction. Neutralization. So whenever they say we've got neutralization, you have to have acid and base. And also remember, neutralizations are always exothermic. Always exothermic. Right. Now with acids and bases, it's actually an ion exchange. The chlorine will go to the zinc to get zinc chlorine, and the hydrogen will bond to the OH and you have water. So you should remember this from grade 10. But if you don't, just check it. Hi. And then what do I know about NH3? NH3 is my weird base. So with NH3, you don't have the plus water. Right. You only have the salt forming. There's no water over there. Right, and then acyl and metal oxide, same thing. Do an ion exchange. The positive of this one goes to the negative of that one. And the last one there, acid and metal carbonate. Carbonate, CO3. Now, if you look at that CO3, for me, if I look at that CO3, I actually see the CO2 in there. Can you see it's got CO2 in there? Right. If you do an ion exchange, the zinc will bind to the chlorine to give you zinc chlorine, right? And the hydrogen and the carbon will actually form H2CO3. Can you see that? But once it forms, it immediately splits into more stable things. CO2 and H2O is very stable. How much water do we have on Earth? Lots and lots, right? Seas full of water. Why? Because it's very, very stable, right? So if it can form, it will form, right? So if you have an equation and you don't know what the products are, if there's H and O, I can sort of guarantee that H2O is going to form. And also CO2, right? Where do you find CO2? Right, CO2. There's a lot of CO2. Why? It's very stable, right? So you have to put them separately. They split immediately because they make more stable products. Right. Okay, I see you need to start doing something. So let's turn the page and go on to page 23. Now you're going to start working. On page 23, I'm asking you to write balanced equations for the following. We're going to write balanced equations for the following. So now I've mixed them up. You've got the grade 10 equations. Just turn back, grade 10 equations. Do you see there's no ions over there on the right-hand side? Because it does ion exchange and you end up with nice new compounds, right? But if something reacts with water, if you've got an acid or a base and it's reacting with water, then what type of reaction do I expect? Ionize or dissociate. And that means then I must end up with charges, right? I must end up with ions. So when you look at this, you have to identify this. Now the first one, they say ionization. They're giving it away. I must end with ions, right? Okay, go and write that equation. got problems. Let's just do the first two and then you can go on. The first one, nitric acid in water. Nitric acid, you have to know the equation the formula by heart. Right. And then I also have to know nitric acid. It's an acid. What do I know about acids? They ionize. So should water go in the equation or not? It should be there because it's going to react with the water to form ions. Right. And how does an acid ionize? It is a proton donor. So it's going to give off an H+. Okay, is this a strong or a weak one? Strong. Ooh, yes, strong. Huh? The big one is to the right. It's strong. So I will end up with NO3 minus and H3O plus, and they are now both in solution. Right. And if you left out the plus and the minus, then they left out the mark. Right. So remember to put it there. Right. Second one, sodium hydroxide. Sodium is Na. Hydroxide, OA, 1 plus 1 minus, the formula is right. Okay, what do I know about sodium hydroxide? Strong base, right. What does a strong base do when it gets into water? Dissociates, right? So it's not going to react with the water. So for this one, you have to just put the water underneath the line. It's not going to make ions. The ions are already present. Right, so it's just drifting apart. So the OH will go one way and the Na plus will go another way. So this is just dissociate, right? It's just dissociating. Then we get to the third one, oxalic acid. What does oxalic acid look like? Well, I prefer COOH. Right, you might even do the other one if you want to, but this is the one that I prefer. And it is going to react with lithium oxide. Lithium is +1 ion, and oxide 2 minus. So I have to take 2 lithium to 1 oxide, so I have 2 pluses for my 2 minuses over here. Right. If you've got problems writing the formula, you should make sure that you know this table of ions there at the back. Eh? So the lithium being +1 because it's in group 1, and the oxide being -2. So you need 2 lithium for 1 oxide. So there we are. Now, is this ionization, dissociation, ion exchange? Ion exchange, right. So what we will have is you've got an acid and a metal oxide. If you want to turn one back, acid and a metal oxide, what do I expect? Salt and water. Okay, so let's make a salt and water. So this one, the hydrogen will be given off and it will bond to the lithium. COO, hydrogen is +1, lithium is +1. It can just replace the hydrogen. Okay, but they will also mark it correct if you wrote Li2COO2, that would also have been taken as correct. Okay. So here they are very lenient, but you have to know what you're doing. Okay, so the lithium is going to there, and what's the other product? Water. Water. Right. So now we don't up with no ions on the right-hand side. Ions on the right-hand side is only when it's in water, because then it dissociate or ionize. Okay, go on from number D. There's just one mistake. Maybe you can just correct that with number H. Just go to number H. It should have been the reaction between lithium hydroxide. Lithium hydroxide. Not oxide, hydroxide. Okay. So start with number D. We number D, ammonia and water. Ammonia, the moment that you hear ammonia, you have little bells ringing, hey? This is the strange one, it does different things. Okay, so if that one is a base, what type of base? This is our covalent base, hey? And it's a weak one. If it's a covalent one, because it's non-metals, it will do the weird thing, it will ionize. So this is the only base that ionizes. And it means I have to put the water into my equation, right? And what happens? Now, how does a base ionize? A base is a proton acceptor. So the H plus is going to be donated to this one. So it's going to become NH4 plus in solution, and you will have OH minus in solution. Right. Next one, sulfuric acid. H2SO4. It's an acid, so what type of reaction do I expect with water? It will ionize, right. So I have to put the water into my equation. Right, now, if we look at H2SO4, can you see there's two hydrogens? It can give off two hydrogens. What do we call an acid that can give off two hydrogens? Diprotic, yes, diprotic. So this is diprotic. So it's actually going to react with two water molecules, and it will end up SO4 2 minus, because two H pluses went away, and then you will have two H3O plus ions, and you can say in solution, in solution. Now guys, there's a little bit confusion about this one. In reality, sulfuric acid is strong and it always gives off the first hydrogen. But then you end up with something that don't always give off the second one. So some teachers like you to write just giving off one. But for all the things that we have to do, all the pH calculations and so on, you have to take it for granted that both hydrogen is given off. So you will have to give off two hydrogen if you want to make use of this one for pH calculations. So it's like when we do electricity. With electricity, you know wires have got resistance. But when we do calculations on circuits, do you take that resistance into account? No, we ignore the wires and we just look at the resistors and the cells. Right. It's the same here. You have to do a little bit of making it easier to do. So what we're going to do is we're going to say if you work with H2SO4, usually you're going to give both hydrogen off, because then you can work out how many H3O pluses we are going to form. There's just one exception to this rule, and that is when they ask me to show the conjugated acids and bases. Now for this I need you to just look on the other side there at conjugated and bases. Remember you did that in grade 11. So let's just go back and see. Grade 11 we said if you had this equation you can show which two is a conjugated pair. What is the difference between the two substances in a conjugated pair? They only differ by one H plus, right? So if you look at the left and the right hand side and you want to see who's the paired with this one, you look at the one that's only one H plus more or less. So this one and that one is a pair, right? And then you also have to say this one is receiving an H plus, so this is a base. That one, if it reacts in the reverse reaction, what's it going to do? It's going to release, to give off an H. That's why that one is an acid. So this one is the base and that one is the conjugated acid. And they may only differ with one H plus. And then the same for water and OH minus. They may only differ with one H plus. So when you get to sulfuric acid, I will usually write giving off both hydrogens, because that's what we need when we do calculations. We have to assume they give off both. But if they ask you to indicate conjugated pairs, a pair may only differ with one H pair. Then I will write H2SO4 and only make it give off one of the hydrogen. Right. And then you end up with HSO4 minus. So if you are doing calculations, pH calculations, you assume they give off both. But if you have to indicate pairs, a pair may only differ with one H+. Then this is an acid, and that is my conjugated base, and they are a pair because they only differ with one H+. Right. Okay. So for this one now, I'm going to write 2. If you wrote 1, I think I will mark it correct. It depends on if you're going to do a calculation. You have to assume it's going to give off both. Right. So let's go on to the next one. Neutralization. What is neutralization? It's an acid and a base. Right. So you need an acid that needs to react with a base, and it produces. Produce means that's what I'm going to end up with. It produces potassium sulfate. Potassium charge +1 because it's in group 1, right? And sulfate, SO4, 2-. So I need 2 potassium for 1 sulfate, right? Every potassium is a plus, so I need 2 potassium so that I have 2 pluses to cancel out sulfates, 2 minuses. So potassium sulfate should look like that. Right, and neutralization. What is the other products that will form? We said neutralization is an acid and a hydroxide, and it will give salt and water. So the other product should be water, H2O. Right. And now, which acid, which base? And this is very important because we have to use it when we get to hydrolysis later on. How do I go back? Now, something is going to supply the sulfate, and something is going to supply the potassium. So actually what you're doing, you think about water as being an H and an OH-, and then you just go back. This one is minus, so it will bind to that positive. This one is positive, so it will bind to that negative. And there you've got it. It should have been H2SO4 reacting with KOH. Right. So you have to be able to find the acid and the base that was used to produce this. But it's just sort of doing ion exchange in backwards way. Right. And now we have to balance it. 2 hydrogen, 1 sulfur, 4 oxygen, 5. Okay, but we need 2 of the potassium for 2 of the potassium over there. And then if we look at the hydrogens, we've now increased that, and there's 2 oxygen. So I have to put the 2 over there as well. So remember to just check if it's balanced. Happy? Right, let's move on. Ionization of oxalic acid in water. Oxalic acid, COOH. I hope by now you know it, even if you did not before today. Right? It's an acid. What type of reaction do I expect if it gets into water? Ionization. Right? It will ionize. So this time, water must be in the equation because I'm going to let it react with the water. Right. How does it ionize? Acid is a proton donor. And what do I have to remember with this one? It's going to donate both protons. So I have 2 waters that it will react to. One receive H from the one side of the molecule and the other from the other side. And I have 2 H3O+. And you may write in solution. Okay. It would have been fine if you chose to do the other one, the H2C2O4, and you had the C2O4 2-. Also correct. Right, next one. Reaction between lithium hydroxide. Lithium charge? Now it is 2- because 2 H+ left. Right. 1 H+ from the one side and 1 from the other. Remember that 2 means you've got 2 of these, and each one is losing a H. Right. Good one. Everyone all right? Okay, so let's move on. Lithium, it was +1 because it's in group 1, right? And hydroxide -1. So 1 lithium, 1 hydroxide, we're perfect. Now this one is reacting with water. Now before you put water, think, what is lithium hydroxide? It's a base, right? Actually a strong base. And what do we know about bases? Bases are going to dissociate except NH3, right? So if it's going to dissociate, don't put water in the equation. It's not going to react with the water. It's already got ions over there. It's just going to go apart. So the lithium is going to one side and the hydroxide is going the other way. Right, very last one. Ammonia and hydrochloric acid. Nothing about water, so this is not an ionization or a dissociation, right? So what's happening here? This is an acid and that is a base. If an acid and a base react, we call that neutralization, and usually it gives a salt and water. But remember, NH3 does things different. So in this instance, this is the base, that is an acid. What a proton is the acid is a proton donor, base is a proton acceptor. So you're going to have a proton donated and accepted. And then you will end up with NH4 plus and Cl minus, or you may even put them together to give you NaCl. Right. Any of this. Right. Okay, so let's go back to the previous page. Now let's just quickly check if your grade 11 knowledge is up to scratch. Now there at the top we have concentration, and tomorrow we're going to do all the mole calculations. So I'm not going to spend time on the mole calculations. We're going to do that tomorrow, right? But the next one is very important, and that is dilutions. How do you dilute something? By adding water, right? But now you have to be very careful. When you dilute an acid, do you do that by pouring the acid into water or by pouring water into the acid? You pour the acid into water. Now think about it. When you put acid and water together, it's exothermic, right? So it's giving off energy. So it's heating up. It might even make that some of that is spattered all over. So you will have, if you pour, you've got a big basin of acid and you put a little bit of water there in and it's heating up and it's splattering all over, what's going to splatter? You'll have acid splattering all over, right? Let's do it the other way. If you've got a big basin of water and you put the acid in there, it's heating up and it's splattering, what's splattering? Most of it is water, right? And if you remember from grade 11, water is very good with storing energy, right? It breaks a few hydrogen bonds and it uses a lot of energy for that. So if you've got water and you put the acid into the water, that water will be very good in absorbing the heat. And then you might even not have a splattering, okay? So you take the water and you put the acid into water, right? Not the other way around. And if you are diluting, you are actually taking a small bit of concentrated acid, and what do you add to that? What do you add to that concentrated acid? You're just adding water, right? You're just adding water. So if you look at this, the moles of acid in your original solution is going to be the same as the moles of acid in the final solution, because I didn't add moles of acid. I only add water, right? So the moles of acid is the same. I just added extra water. And then if you remember, C equals N over V, and therefore N equals C times V, and that's where that equation comes from. So you have to remember, the moment that they tell you they are adding water to dilute something, you have to use this equation. And it is not on your information sheet, right? It's not on your information sheet. Now, the guys who don't remember about dilution, what do? They take the titration equation. And even if you get the right answer, they give you 0 marks, because it's not a titration, it's a dilution. It is already 1-to-1, right? So whenever it's a dilution, you have to remember to put that. So if it's water they add, you will have, if you write the equation, ionization and dissociation. If you have to do a calculation, it is a dilution one. Right. And the catch in this one is you sometimes forget that the volume over there is not what you added. The volume over there is the total new volume, right? The new volume on this side is the original plus the water that you added. Right. To see if you understand that, turn the page and do 2.1 on page 24. 2.1, page 24. Can you see volume is on the left-hand side, but volume is always also on the right-hand side? So it doesn't matter if you're working in cube centimeters or cube decimeters, it will cancel out. Just make sure you don't put cube centimeters on one side and cube decimeters on the other side, then you'll have a problem. Right. So any unit, but the same one on the left and the right-hand side. So here I would have said how much water must be added to 30 cube centimeters of a 0.2 HCl solution. So I start with a 0.2 solution and I have 30 cube centimeters of that. And then they say I want to change the concentration, so afterwards the concentration should be 0.03. And then I get the new volume, 200 cubed centimeters. And is that what they asked me? No. They did not ask what is the new volume, right? They asked me what must be added. So if I know what is added, then I will say I have to end up with 200, but there was already 30 in the container. So I only had to add 170 cubed centimeters. Right. So that is often one of the first questions when you get to titrations, for instance. They have you calculate a new concentration or asking how much water to add. Right. I would like you to go on with 2.2 next. 2.2, they tell you a solution of acid HX with a concentration of 0.15 is prepared. So they have H, and they're telling you it's an acid. And they say the concentration of the hydronium ions in the solution is 3.2 times 10 to the 6. And now they ask you, write an equation for HX and water. So we start off, HX and water. HX, they told us it's an acid. So what type of reaction do I expect? Ionization, and I have to put the water in there. Right. And what will happen? Now, I don't know if it's weak or strong yet. I'm just going to say acid is a proton donor. So the proton will be donated, and you will end up with X, and there definitely must be a minus over there. And then this one will become H3O plus in solution. Right, so you have minus and plus, just check that one. Right, and now we get to the second part, and the second part is the more interesting part. They are asking, is this a strong acid? And the answer was? And the answer was no. Right, okay, let's talk about this. What is your definition of a strong acid? Ionized completely. So if I made a solution and I put 0.15 into every cube decimeter, and it was a strong acid, how much of the H3O plus would I have expected? 0.15. And what do they tell you? They tell you there's not 0.15, there's only 3.2 times 10 to the minus 6. So only a few of those that you put in actually went over. So the answer is definitely no. And I will say that because the H3O plus concentration is so much smaller than the HX that I put in there, right? That shows me that it ionizes incompletely. It ionizes incompletely. And now they're asking us to name the conjugated pairs. Now, what do I have to remember? A pair only differ by H plus. So if I look at HX, who is paired with HX? HX and X minus, right? They are a pair. And who's paired with H2O? H2O and H3O plus is a pair. Right, everyone happy? Okay, so that was grade 11. If you turn back one page, you finished with grade 11. And I think we're ready now to move on to grade 12. So what we are going to look at is the O2 protolysis of water and also the pH scale. Now, let's think about water. Water, we call it an ampholyte or an amphoprotic substance. Tell me what's an amphoprotic substance? Yes, something that can either react as an acid or as a base. So let's take a reaction where one molecule acts as an acid and the other one acts as a base. So the acid is a proton donor and the base is a proton acceptor. So what will happen? We will end up, this one will become OH minus, and that one will become H3O plus in solution, in solution. And that's why it called it O2, right? Because it's water with itself. Protolysis because it's transferring a proton, right? Electrolysis will be an electron that is, this is protolysis, it's a proton that is donated. Right, so we have that one. Now, if I want to write the Kc expression for that one, what should the Kc expression for that one look like? It should be OH minus times H3O plus concentration divided by 1. Yeah, nothing, 1. Okay, right. Because these are pure liquids. They don't even come in. So your Kc equation looks like that. Now tell me from Monday, what influences my Kc value? When will my Kc value change? Temperature, temperature. Right, temperature. Now, if you look at your page with information, that orange one, you will see there you have this, but they've now exchanged that small c for a W. Water is so important. You are actually 70% water, so it's very important. Huh? Water is so important, we're going to change that C to a W, and we call it KW value. And if you look at, come on guys, over there. Right, attention. If you look at this one, it gives you KW. There you've got your KW equation. And where does it give you afterwards? It tells you that if you are at 298 Kelvin, which is the same as 25 degrees Celsius, because you subtract 273, do you remember? Right. So if you are at 25 degrees, then the Kc value is 1 times 10 to the minus 14. 1 times 10 to the minus 14. 1 times 10 to the minus 14. But that is only true when you're working at 25 degrees Celsius. And the reason why they chose 25 degrees Celsius is we want to work in the lab without always making things cold or making things hot, right? We are usually at more or less 25, so it's easier if we just learn one of them by heart. So this is the one they give you. If they want you to work at a different temperature, they have to give you a new KW value, right? So we look at this, KW, 1 times 10 to the minus 14. Now I want to ask you, is this a big or a small one? Is this big or small? This is very small. So if I take this water in this bottle and I was able to count which of these H2O molecules in there occur as molecules and which of them have split up into OH minus and H3O plus. How many of them will be H2O molecules and how many will have split up into ions? Nearly nothing is in the ionic form. Once you take the ions in there and you multiply it, you get 1 times 10 to the minus 14. So if you drink this water, there's more or less no ions in there, right? No H plus and OH minus due to the water if it's pure water. You only have H2O molecules more or less. Little bit. Once you've multiplied them, you get that very small 1 times 10 to the minus 14. Now if I have pure water, pure, how does the OH minus and the H3O plus concentration compare? Come on, it's pure water. No one else put OH minus or H3O plus in there. Then there will be 1 OH minus for every 1 H3O plus. Everyone happy? Okay. This means those two are exactly the same, and I can say that H3O plus squared. Because they're both the same. I can just say it's squared. And then if I go and work this out, H3O plus, I will end up with 1 times 10 to the minus 7 moles per cubic decimeter. So I can ask you, what is the concentration of H3O plus ions in pure water? It's little, hey? 1 times 10 to the minus 7, 0,000, stop me, 1. Right. So there's very little. Okay. So the first thing you have to remember is that KW equation. We're going to use that whenever we are in solution and we want to go from OH minus to H plus or from H plus to OH minus. We're always going to do that with the KW expression. Right. And then the last thing is pH. pH, if you remember, is negative the log of H3O plus. Right. It's the potential of hydrogen. You get other things like PCl. It's the potential of chlorine, POH. So there's a lot of P things, but we're only doing pH. It's the potential of hydrogen ions in there. So it is negative the log of H3O plus. And now, if I've got pure water, what do I know about H3O plus in pure water? In pure water, that is 1 times 10 to the minus 7. And if you work it out, you end up with 7. Right. So pure water's got a pH of 7. It was not chosen. It worked out that way. Right. Pure water has got a hydrogen concentration of 1 times 10 to the minus 7. Therefore, it's got a pH of 7. Right. Now, we're going to do a lot of calculations with things like this. But if you go into your summary, I will see on page 21. If you go to page 21, you will find this diagram over there. The diagram is supposed to help you. The diagram is supposed to show you how to get whatever you want. So if for instance tell you you've got an acid and they give you the concentration of the acid and they ask you the pH, you start by saying for pH I need the H3O plus concentration. Right. But that is not necessarily the same as my acid. If my acid is HCl, what do I know about HCl? It's a strong acid, right? And then if I write it down, how does HCl react? HCl, it's a strong acid. That tells you that it will, strong acid, it will ionize completely, right, completely. So if you look at what happens, if it ionizes, it will give Cl minus and H3O plus, and then you can say, aha, it ionizes completely, and for every HCl that I start off, I end up with H3O plus. One of these will make one of those, right? So if they told me I've got an HCl concentration of, say, 0.3 moles per cube decimeter, then now I can say, okay, so therefore, my H3O plus concentration is also 0.3 moles per cube decimeter. Because I know every single molecule is going to do that, right? Because it dissociates, ionizes completely. And I know it's only making one. So if you think about your strong acid, HCl, how many hydrogens is it going to produce? 1. HNO3, 1. And H2SO4, 2. So the only ones they're going to ask you the pH are your 3 strong acids. And if it's HCl, it will give you 1 H+. So their concentrations will be the same. If it's HNO3, then obviously it's also only giving 1, then their concentrations will be the same. But if it's H2SO4, then they're in the 1:2 ratio. Right. Okay, so just remember, concentration of acid is not necessarily the concentration of the H+. Sometimes you have to get it. And now, how about a base? If they give you a base, what do? Base, they can only give you a strong base. Strong base will give you OH. How do I go from OH to H+? Kw value, right. How do I do that pH? Just put it into the equation. So it's not that difficult if you have the sort of the layout of the land, how you're working. Okay, let's see how you fare on that one. On page 24, once again, we're going to do 2.3. Can I quickly have a show of hands? Who's IAB? Okay, you don't do pH calculations. So just leave number C, just do up to number B. if something is wrong in the exam paper, you don't go falling apart because it's not your problem, right? You do your best with what they give you. You write there, I need the volume or whatever, right? Or you say, I assume I am using volume this or whatever, and you go on, right? Because if there's a problem in the exam paper, they will give you the marks. So don't go feeling all shattered, right? If something is wrong in the exam paper, oh, wonderful, they're going to give me the marks. Continue with the rest. Okay. So in this instance, there was a typing error. There had to be 300 cube centimeters. So it was x cube centimeters of water is added to 300 cube centimeters of a 0.15 mole per cube decimeter sulfuric solution. Yes. So there was no way to know that except if they gave it to you. Right. So if they gave it to you, you put it in there, and then you would have worked it out, and it would have been 1,000 cube centimeters. And then you said, okay, but what should I add? I have to end up with 1,000, but I already started with 300. That means I had to add 700 cube centimeters. Right, but that was just revision. Okay, I think I'm going to give you a few seconds now because you couldn't go on because you couldn't do the first one. Just go on and see if you can do B and C. I am asking for the hydronium ion concentration. They're giving me sulfuric acid. Now, whenever you change from substance, you're supposed to have a ratio somewhere. So the first thing I'm going to say is, what do I know about H2SO4? It is a strong acid, and therefore I can assume that it will ionize completely, right, completely. And how does it ionize? It will ionize by giving off 2. So I will end up with SO4 2- and 2 H3O+. And that shows that the H2SO4 to H3O+ ratio is 1:2. Right. So if the concentration of the solution, right, and we're working with the final solution, the concentration, I think you should add that final just not to make it ambiguous, to make it clear. If we're working with 1:2, then what will be the H3O+ in the final concentration is 2 times the 0,045, which is 0,09 moles, thank you, moles per cubed decimeter. Right, so that was the question. They asked me, okay, we now have this concentration. Yes, sure. Right, we started off with a 0.15, and we diluted it, and now we ended up with a 0.045. And now this is a sulfuric acid. So what we have is now we have the concentration of the sulfuric acid is 0,045. Is that what you wanted to ask? Right, because the important thing is the concentration of the acid is not always the concentration of the H+, right? So what do we know about the acid? We know it is strong. That means everything is going over. And then, how is it going over? When it is reacting, it is producing 2 H3O+. So the H2SO4 to H3O plus is 1 to 2, and therefore, perfect. Thanks. Okay, so that is the second one, number B. And then the very last one is easy. They're asking pH, it's just putting it into the equation. And if you have negative the log of 0.09, then you end up with 1.05. Is that what you would have expected? What do we know about sulfuric acid? It's a very strong acid, and a concentration of 0.09 is actually still strong. Eh? So you've got a lot of it, and all of it will give you H+, and each one will give you 2 H+. So you end up with a lot of H+. Right, now this was for an acid. Let's see if you can do the same thing for a base. So you can move on to 2.4. I will leave it here if there's someone who's writing. Move on to 2.4. Depends on the rounding. Right, just quickly do number A together. Number A, they ask you if they have 0.5 grams of lithium hydroxide and it's used to prepare 200 cube centimeters of solution. And now they ask you calculate the concentration. Now, we're going to do a lot of mole things tomorrow, but you should have this one from grade 11. Right, to work out the concentration, small m is the mass that they gave me, 0.5. Big M is the molar mass. Where do I find that? Periodic table, right, periodic table. We're working with lithium hydroxide, so you just add together all the masses and you will get 24. Right, and then what's the catch? Volume. There's only one volume in this one, right? If there's only one volume, then that volume should be in cubed decimeters. So I take my cube centimeters and divide by 1,000. Then I end up with cube decimeters, right? And if you do that correctly, you end up with 0.10, actually 4, and that depends. If you're rounding off, you can leave it like this, or you can use the 4. It will make a little bit of difference in the funnel, but they mark both, right? So, do you want to leave it like this? Okay, nice, okay. Mole per cube decimeters. That was for A. Now we have the concentration of lithium hydroxide. So this is for lithium hydroxide, the concentration. And now in the second one, they ask us, what is the concentration of the hydroxide ions? Now, what do I know about lithium hydroxide? Strong base. You see why that first table is so very important, right? It's a strong base. And what do I know about a strong base? It dissociates completely. And just show me how it dissociates. Now, dissociate, should water go into the equation or not? Nope. So it will make a lithium plus and it will make OH minus. And you can put aqueous there if you want to. Right. So what does it show you? It shows you the lithium hydroxide to OH minus. One of these will produce one of those. And immediately I know, okay, so my OH minus will also be 0.10 moles per cube decimeter. Because every single one that I put in will make an OH. They react completely. Okay, and then just to make things more interesting, with C, I ask not the hydroxide, but the lithium ions. Well, I've already written the equation. If I produce one of those, I also produce one of those. So they've also got the ratio 1:1, so that answer will also be for the lithium ions. It will also be 0.10 moles per cube decimeter. Same thing. Right. Now we're up to number D, hydronium ion concentration. I've got OH and they're asking H3O+. How do I go from H3O+ to OH minus? KW. So it's a quick. Whenever you want to switch between H3O+ and OH minus, we're going to work with KW. Now, if they should actually tell you that they're working at 25 degrees Celsius. But if they don't tell you, just assume that you're working at 25 degrees Celsius, so that you can use KW is 1 times 10 to the minus 14. And I'm looking for H3O+, and the OH minus I already have, 0.10. And then you get your H3O+ concentration as 1 times 10 to the minus 13 moles per cube decimeter. Right. Now, if you haven't rounded off there at the top, if there at the top you left it as 0.104, then you would have ended up here with 9.62 times 10 to the minus 14. It looks a lot different, but it is actually not. Right. So it depends on your rounding. Right. If you round it off to 0.10, you will end up with 1 times 10 to the 3. And then pH is just putting it into the equation. Negative the log of the H3O+, negative log of 1 times 10 to the minus 13 to give you a pH of 13, and if you haven't rounded, you would have ended up with 13,02. Is it getting better? Yeah, it's not that difficult. Whenever you have H plus and you're looking for OH minus, KW, right. Can you do anything with the pH other than get the H3O plus concentration? No. So if you come into a strange question and you have a pH, put it into the pH equation and get the concentration of the H plus. Let's look at the next one together. Now, sometimes you've got a few calculator problems. Going back. Now here they give you the pH. They don't give you the concentration and ask the pH. They give the pH. So we have to move back. pH, negative the log of the H3O plus concentration. And now they give you pH. They give you that side. Okay. Now, if I want the H3O plus, the very first thing is to take the negative over to the other side. So you get negative 11,61 is equal to log H3O plus. Right, so I took the negative over. Now I want to take away log here. If I take away log on this side, I have to add a 10 underneath there, because that is what log means. Right. What is the number if we have it to a ground of 10? Right. Now, how do I do this on my calculator? I will say second function log of minus 11,61. Second function log, right? You want the inverse of log, second function log of minus 11.61. And then you should get your H3O plus concentration as being 2.45 times 10 to the minus 12 moles per cube decimeter. Right. Is your calculators agreeing? Yes, it's not that difficult. Right. So remember, you're taking the negative over, because some people forget about the negative and then everything goes haywire. Right. So, but have we answered the question? Well, we've calculated H plus, but we haven't calculated OH minus. How do we get OH minus? KW, nice. Assuming we're at 25 degrees Celsius, right. Now the next part of acids and bases are actually titrations. But I'm not going to do titrations today. That's actually mole calculations. So tomorrow when we do mole calculations, I will talk about titrations, and we will do titrations, and specifically where you have a second equation. Sometimes they do something with an excess acid, and then they do a second one to determine by titration how much is extra. So that we will do tomorrow. What we still have to do today, the very last part of acids and bases, is hydrolysis. And that is on your very last page there of acids. We are going to look at hydrolysis. Right, now with hydrolysis, you can be sure they're going to ask it. They're going to ask it at least for 1 mark, maybe a multiple choice question where it's 2 marks, or they can ask a longer one where it's 3 marks, but I can more or less guarantee at least 1 mark in one of your exams will be hydrolysis. Right, maybe more, I think more. So we always start off with the definition. Hydrolysis is a reaction of a salt with water. So it is when you put something into water. Now, say for instance you start with HCl and you put NaOH there. What will the products be? HCl, NaOH. Products will be sodium chloride and water. Right. Now when we do this, we are adding an acid and a base. Is this acid a weak or a strong acid? Strong acid. Base? Strong. Right. And now if I've got a strong acid and a strong base, they are going to neutralize each other. And what will the pH of the final solution be? That one should be more or less a pH more or less of 7. Right. If it's strong and strong, you will end up with neutral. If the acid is strong but the base is weak, it ends more to the acidic side. And then you will end up. Okay, so you know about that. Now, eventually, if you look at this, you added everything together in a beaker. And what did you get in the beaker? You actually got a salt solution. Right. And what is the pH over there? The pH is 7. And now they're going to ask you a question. They're going to say, okay, say for instance, I took water, pure water, and I just added sodium chloride into that water. What will the pH of that solution be? And the answer is also 7. It doesn't matter if I prepared it by adding an acid and a base together to get the salt solution, or if I made it by just adding the salt into water. It doesn't matter. I have a salt solution and therefore the final product will be like that. Right. So in future, they're going to give you other ones. They're going to say, for instance, if you take ammonium chloride, they're going to ask you, if I put ammonium chloride salt into water, will that be an acidic, a basic, or a neutral solution? And now I have to say, okay, it doesn't matter if I put the salt into water or if I make it by using an acid and a base. So let's go and think, what acid and base should I have used to make ammonium chloride? What acid? Hydrochloric acid. What base? NH3. What do we know about this acid? Strong. What do we know about this base? Weak. So that means the acid is winning. So if I put this into water, it will be an acidic solution. Right. Okay. Go to your books. Let's see how you do this first part. Right in the middle of page 26, you've got this table. Right? And I ask you to give the formulas of the acid and the base that can be used to prepare the salt and indicate if the solution is acidic, basic, and neutral. Right. So you have your compound, and sorry guys, here's a typing error once again. It should not be acidic, it should be what acid must be used, right? What acid must be used, then what base must I use, and what type of solution will I end up with. Now let's talk about the first one, ammonium nitrate. Ammonium nitrate will be NH4NO3. Ammonium plus 1, nitrate minus 1. Okay, so if they ask me that one, which acid should be used to prepare that one? Nitric acid. What do you know about nitric, strong or weak? Strong. Which base should I use to prepare ammonium nitrate? NH3. You can see it inside there, NH3. And what do we know about that one? Weak. So who's winning? Acid. So this will be an acidic solution. Next one, potassium chloride. Acid, hydrochloric acid, which is strong. Base, something that gives me the K, KOH. What do we know? Strong. Strong, strong, neutral. Right, sodium oxalate. Right, oxalate. Which acid should I use? Oxalic. You've learned something today, eh? Yeah. Good. What do you know about oxalic acid? Weak. And that sodium comes from sodium hydroxide. Strong. Who's winning? Base. So this will be a basic solution. Right, we get to ammonium carbonate. Now this is difficult because ammonium, if you wanted to write it, ammonium NH4, but you'll have to have 2 of those because they are only +1. And carbonate is -2. So 2 ammonium to 1 carbonate. Okay, so which acid? The one that will give me the carbonate. So it should be carbonic acid. Right, carbonic acid. H2SO4, H2CO3. What do we know about that one? It's weak. It's not one of the 3 strong ones, so obviously it's weak. Hey? And then we get to ammonium. What do you know about ammonia? Weak. Weak, weak? Neutral. Right, sodium sulfate. Okay, but there's something, not sulfate, sulfite. What is sulfite? SO3, not SO4, right? So you have sodium, and you will have 2 sodium to 1 sulfite, because it's 2 minus. Right, which acid? H2SO3, SO3, right? Alite. What do we know about that one? It's not sulfate, so it's not strong, that's weak. And we put that with sodium hydroxide, and sodium hydroxide? Strong. And we end up with a basic solution. Right, we get to lithium carbonate. It's a carbonate once again, so it will be H2CO3 once again. Carbonic acid to give you the carbonate. What do we know about carbonic acid? Weak. Lithium hydroxide? Strong. Who's winning? Base. It's basic. Right. Sodium acetate? Acetate comes from acetic acid. CH3COOH. What do we know? Weak. And sodium hydroxide? Strong. Basic. Okay. But unfortunately, this is only 1 or 2 of the marks. Because once you've done that, they're going to ask you to explain. Okay. You can see it's nearly 1 o'clock. Hey? Right. They're going to ask you to explain by using equations, why is this one making the water basic, acidic, or whatever when it gets into water. Now, I want you to think back. If you think about hydrochloric acid, what do we say about hydrochloric acid? It's strong acid. So if HCl reacts, let me just put that aside. If HCl reacts, you end up with Cl minus and H3O plus. What do you know about HCl? Strong acid. Strong acid. Right. Who's the conjugated paired with that one? Who's conjugated paired with that one? Cl minus. They only have to divide by 1 H plus. Right. So this is the conjugated base. Now, if this acid is very strong, what is the definition of strong? Ionized completely. So every single one is going over to Cl minus. Do you then think the Cl minus will be coming back? No. If this one is a strong acid, then its conjugated base will be very weak. It will not be going back. Something that is strong wants to sit up in the split up form. They don't want to be combined. That's why it is a strong acid. It wants to split up. So if you put chlorine into water, chloride ion, chlorine is what? Cl2, right. Chloride ion into water, it will not be doing anything because it is happy the way that it is. It wants to be split up, right. So what we're going to do is we're going to say, okay, let's take this example. You've got ammonium chloride. First, just for 1 mark or 2 marks, they're going to ask you, is it acidic or basic? You can say, okay, this comes from ammonia, and this comes from HCl. Weak, strong, acid is strong, it's going to be acidic. There's your mark or 2, right? And then they're going to ask you to explain. And when you ask you to explain, you're going to take the ions separately. Right, I'm taking the chlorine. What do we know about chlorine? It comes from HCl. What do we know about HCl? It's strong. It wants to be split up. So this one, you just write, it does not hydrolyze. And then you get to the NH4. What will the NH4 form? Where does the NH4 come from? NH3. And what do we know about NH3? It's weak. So a weak one will be going back, because its conjugated pair is strong. So if it wants to make something that is strong, it will not react. If it wants to make something that is weak, it will react. And now I want you to turn back just 2 pages to the bottom of page 22. And there I have a table that will help you. If I put a salt into water and it's got a chlorine ion, what will happen to the chlorine ion? Perfect answer, nothing. Right, nothing. Because the Cl minus comes from a strong acid. So this is a very weak base. It will not react. So it will just drift around. So it will not make it basic or acidic. It will just drift around. How about SO4? Where does it come from? SO4 2 minus comes from sulfuric acid. Strong acid. So the SO4 2 minus is very weak. It won't react. So for all of those that come from something strong, they will not react. The same thing for the sodium, potassium, lithium. They will not react. But if you get to these guys, they come from something that is weak. So they are actually strong and they will be going back. So if you get the carbonate atom, where does it come from? Actually from carbonic acid, right? So it will start going back. It will. And now, what is the definition of hydrolysis? Reaction with water. So don't start putting OH minus and H pluses or something strange in there. It's reaction with water. So you take your iron and you take water, and now you know where it's going. If it's CO3, it's actually going to H2CO3, carbonic acid, but just go let it one step at a time. So it's taking up 1H, and if it takes up 1H, then that will end up as OH minus. And that would be why that will make a solution basic. Right. NH4 going to NH3. How can it go to NH3? It needs to give off the H+. So that's why the water ends up H3O+, and that's why it will be acidic. So let's just go and do that very last one. On page 26, final one for today. Sodium oxalate. What does sodium oxalate look like? Oxalate, COO, 2 minus, or you can put the sodium in there, 2, right. Sodium oxalate, or you can put the sodium in front. They will take that as correct as well. Right. Dissolved in water. And now they want to know, is it acidic, basic, or neutral? So where does the sodium come from? It comes from sodium hydroxide. And where does the oxalate come from? Oxalic acid. Right, what do you know? The base is strong, the acid is weak. So it's going to end up basic. So for this long question, that would have been worth 1 mark. It's basic. Right, and then they ask you to use equations to explain the answer. Use equations to explain the answer. Now, I'm looking at them separately. I'm looking at my sodium ion in there, and I'm looking at my oxalate ion in there. Right, what do you know about sodium? Where should it go? It can go to NaOH. Will it go to NaOH? No, NaOH is strong. So this one is weak. It will not hydrolyze. Right, so it will not hydrolyze. And then we get to the oxalic one. Now, it's going to react because this comes from a weak something, so it's going back. Weak one, want to stay together. It is hydrolysis, so you have to put in water here. And it is going to COOH2. It wants to go back to the weak state. Right. So you'll have to have 2 water molecules, and what happens when the H is transferred to there? That one ends up as 2 OH minus. And this is why it is becoming basic. Because when this oxalate ion comes into the water, it will hydrolyze and it form OH minus, and that will make it basic. So if you find it difficult to write the equations, just turn back and reread that table. Because there I gave you most of the equations that you might need. Right, it's all there. Have you learned something today? Right. So guys, tomorrow we're going to look at mole calculations. But now I want to ask you, if you really have big problems with moles, I want you to go and look a little bit at moles this evening, because we have a lot of work to cover tomorrow. We want to start with the basics, but we want to go up to really difficult ones. So I can't spend too much time on the basics tomorrow. If you have really lots of problems with basic moles, just go and check it. Right. See you tomorrow.